first of all, a bit mouthful, the title. But I explain later on what this is about, sample quality and subject dependency. So I'm Norman from University of Surrey in the Department of Computer Science. So as a computer scientist, we're interested in developing algorithms, looking at measurements and quantifying intervals. So this is currently my area of interest. So this is University of Surrey. It's about under 40 minutes from London. And I always welcome day visits or short-term visits. I got quite a few visitors coming over working with me at the moment. So you're all welcome to give a talk or just to say hello. Okay. Here's my little research team. It's part of the bigger group in the computer vision team. I work mainly on biometrics, but also on data analytics, on healthcare analytics. So got interest here. And also got some funding from Cybersecurity Malaysia and Medical Research Council, working on the healthcare modeling side of the things. But today's topic is mainly on the biometrics. Okay. And here are some of the topics I work on. For instance, facial anti-spoofing detection. So my student and I developed an algorithm called dynamic mode decomposition, and we are able to take video as input and then recognize whether the video is actually a replay attack or a photo attack. So for instance, a photo attack will give you a blur image that doesn't look like a face at all. Okay, so this all relies on modeling of the dynamics. But that's not the main topic I want to focus on today. I really want to talk about subject dependency, sample quality, and perhaps throw in a little bit of latest topic on the spoof attack and how these different factors affect the performance of the system, as well as how do we mitigate some of these adverse factors such as spoof attacks and bad quality samples. Okay, so these are the main topics I want to talk about. And the first one is on the subject dependency on in the influence of subject on the performance measure. So come back to the very basic. Biometrics is really about comparing a template with a query sample through a matcher, and then you get a matching score. If the identity of the two samples are the same person, we accept, but otherwise we reject the identity claimed. But this is just under zero effort attack. That means you are just comparing whether the person is the same or different, and there is no active attack on the biometric system. Okay? So far so good. So let's just keep to this scenario first. We have a bunch of positive samples, a bunch of negative samples. From there we estimate the distribution of the genuine scores and the imposter scores. That's what we call them, or match score, non-match scores. And after that we just calculate the integral to the right and to the left. Then we get the false non-match rate and false match rate. So again, that's the very basic things we do in performance evaluation. Always calculate the intervals, the cumulative density function of the two distributions. Okay, and from there we plot the false match rate versus false non-match rate curve in terms of ROC and detection error trade-off curve, which is just happen to be a nonlinear scale. Okay, that's the very basic. And I'm interested in looking at the performance. So our target when we measure the performance is really to look at the matching score. Yeah. Whether it comes from same person or different persons. Can you tell me how many factors are there that could affect the template or affect the query or affect the or affect the biometric measure? How many factors are there? Okay, 3, 4, 5, many. That's correct answer. So you got a lot of factors. There will be the user demographics of the target users that constitute the template. That's an important factor. Skills of the operator, the quality of the template, and the sensor itself. And at the query, and so when the system is operational, for instance, in the border control, you have different types of sensor there, and the sensor might be different from the one that was used to create the template. So then you have a mismatch in the sensor. You have the session variability over lapse of time, 3 years, 5 years. Down the time, we see that the performance may change. Okay, and the demographics of the imposter, the environment where the system operates, as well as the application scenario. So for instance, covert versus overt recognition, the level of user cooperation, and whether the device is mounted on a mobile device or phone. For instance, that would be very challenging for face recognition if you do it on a mobile phone. Okay, but that's not the end, not the factor. The other factor is the stochastic nature of the algorithm. That is another factor, not important, but still one factor. And the other one is the design population of the biometric database. But if you think about it, we try to measure the performance based on the matching score, and there are so many factors we have to take into account. So you could see how challenging it could be just to quantify the correct performance. So giving a number on the performance of the system is actually quite tricky. I'll give you an example here. So here is the XM2 VDS face database, which Sarah has developed a very few years back. We have 200 users, 200 genuine users, and for each, or 200 templates, if you think about it. And if you take one of the 200 templates, match it with the query samples, and there are 3 of them, so same person, and we estimate distribution, and we just put it there. Okay? And if we do so and then we match the template against 400 other imposter users, so other user than the person itself, and we get 400 scores. And then from there, we estimate distribution. But that's for the first template, yeah? Okay? So if you do it for and we call the, okay, just forget about this. And if I use the second, if I use another user, so J is 2 now, you see the distribution is different. Yeah? So for the first user, I would have put the threshold around 2, right? That's a better decision threshold. And for the second user, probably I want to put it around here, like this here. Okay? So, and if I continue on for the third user, the fourth, and then more and more, and it's getting really busy. Okay? So, it shows that, if I know what the threshold, if I set threshold in a user dependent way, maybe I can make a better decision. Okay? But it also shows that it's very challenging to find a threshold that suits everybody else. One of the challenges here is that we don't have enough training samples to even to reliably estimate the threshold. Okay, but it shows it highlights that the subject has clearly an important factor in influencing the system performance. Okay, and the global distribution is the dark dash line here we see. And they are clearly not Gaussian, not normal, because they are a mixture of different components, yeah? Okay? And I've done experiments here. So if you have 200 target subjects, and we create the bootstrap. So if you bootstrap the user, each time draw a number of templates, and then you reconstruct the experiment 100 times. What you get is a video that looks like that. So you can see here, you get different curves, and this is a dead curve. You can see the performance actually varies. There's an interval. There's a clearly confidence interval in the curve there. Okay, and from there you can find the mean, median, the low bound, and upper bound. Okay, so it clearly shows that the user is an important factor in influencing the system performance. So remember, next time you look at performance curve, it's not one curve. It could have been a number of curves, but you happen to see just one particular curve. Okay? So there's a subject dependency, and the question is, what can we do about that? So here comes the mitigation strategies, yeah? So one of the approach that I have developed in my PhD is, okay, I've got 2 users here, and they have different mean and different distributions, yeah? So what I did is project them to normalize against the imposter distribution, such that you only have to worry about the genuine one, which is slightly different. Okay. The other approach is, of course, project the distribution such that the mean of the imposter and the clients are common, and the mean are exactly the same for everybody else. Okay, that's called F-norm. Rather than going to the details, I provide the references here if you want to know more about that. Okay. And okay, a lesson here to learn is, okay, if I can create a user-specific, what I call score normalization, that's what we've done, yeah? But you can also think about user-specific features, user-specific model, user-specific threshold, or user-specific fusion. So let's just look at one of the approach here, which is user-specific score normalization. in a two-dimensional space, you have a face system and a speech system there. And each cross here is from one subject, but from the data pulled from the face and the speech at the same time. Okay? So you can see that the dots are in all over the place. They're very busy. This is what the multimodal biometrics trying to solve here, trying to find a decision boundary separating the positive class from the negative class. Yeah, that's what we do. But if you use a user-specific approach, you're actually trying to align the cross to be in the common space. So the mean of the imposters, they are all centered at 0, precisely at 0. Whereas for the genuine scores, it's very difficult to project them exactly to 1, 1, coordinate 1, 1, because we do not have enough training samples. But with the F norm, we actually can push them to be more compact, and as a result of that, we can get performance improvement. Okay, and the improvement for one particular system could be the error rate originally is 0.57%, and then we can actually halve the error just by doing that in a multimodal system. Okay, that's user-specific fusion, and we run 15 experiments and show that actually that approach can be quite effective. Okay, so that's the mitigation strategies. Now let's look at sample quality. We know that biometric samples affect the system performance, right? Bad samples results in worse performance. So, but there are a lot of assumptions there. What are we measuring? What's the assumption behind? Okay, so that's the normal zero effort imposter here, and this is a normal genuine score in the distribution in the normal condition, normal expected operational conditions. Okay, under spoof attack, this is a non-zero effort, so the imposter has to put some effort. For instance, doing a replayed video attack, and so down the imposter score is now moving closer to the genuine score. So you can see that suddenly the performance of the system dropped significantly. Okay, or if your system operates in adverse conditions, noisy conditions, then the genuine scores actually drop, moving closer to the imposter. Okay, so you can see immediately why the system performance can drop. So this is a fingerprint NFIQ. So people doing fingerprint minutiae testing, and NFIQ use different gradings from 1, 2, 3, 4, and 5. Yeah. So 1 is the highest quality, 5 is the lowest quality. So what we did here is that in the highest quality, this is false non-match rate. It's from the genuine score. So you get curves like that. So this is the best performance curve because the zero effort imposter is actually here, and the genuine cumulative density function. This is a false non-match rate. So if one goes like that, the other one goes this way. Yeah. So the further they are separated, the better. So you can see that at quality 1, you have better performance. At quality 2, you degrade, and then this is medium upper quality, medium lower quality, and then we call this lowest quality. And the separability is very narrow here. Okay, so that no surprise if you plot the performance, you see that with the highest quality you have a good ROC curve, so lower left corner is a better one. With low quality tendency, so here we mix the 53% of samples are high quality, 27% of medium high, 13% medium low, and only 7% low quality. So I created a mixture of data such that the database you have here, most of the samples has high quality. Okay, this is a scenario when your sample has a lot of 50% of them have low quality samples. Okay, so if your database is dominated by low quality samples, you have this. Your ROC curve is actually getting very bad at the top there. Okay. Then also, of course, we can also create a scenario with a mixture of high quality and low quality in equal proportion. Then you have a curve that is slightly in between the two of them. Yeah. So we created an algorithm to simulate the curve, so you can now control the mixture and find what's the correct mixture for your operation for your operational scenario. Okay. So that's an algorithm that's trying to generalize that curves across different application scenarios. Okay. So far, if you have a database, you only get one curve. But the message what I'm trying to say here is that you have a database, you don't have to be stuck to one single curve that is dependent on the database. You could actually sample the data such that some of the proportions have high quality, some of the proportions have low quality, and hence you can generate a range of curves that will match your operational scenario. Okay? So that's the idea of generalizing the dead curve. And spoof attack as well will give you different performance curve. In this case, this is a spoof attack using different material. If the zero effort attack gives you this curve, the spoof attack is actually moving closer to the imposter. So moving closer to the genuine score here. This is which results in false non-matched red. Okay. Again, this is a better curve. As the spoof false matched red moves to the right hand side, you get worse performance. Okay. Probably you don't get used to looking at performance curve this way, isn't it? It's just a different way of showing the same thing. If I show you in the rock curve, you say, aha, that makes sense. Okay, but actually that rock curve came from this kind of data first. Okay, but it reveals a lot more information. So under zero effort attack, you can see that the rock curve is very close to the lower left corner. Under spoof attack, your system performance it's terrible. It's almost unacceptable. Okay, but in real life, we don't have just zero effort attack. You can expect some of the spoof attack, but that could be only 1 or 2%. And here what I'm trying to do is to simulate that they're actually 50% of the spoof attack, and you can see the curve is actually unacceptable. Okay, so by understanding the various behavior, perhaps you can quantify this biometric system performance in a much more realistic way. The question is, what's realistic, right? How many proportion of the attacks should be zero effort? How many proportion of attacks should be considered spoof attack in a real operation scenario? How many? It's a very difficult question to answer. Even putting the proportion, it raises a lot of questions. Okay, so that sort of shows that clearly we need to consider different factors when we design the biometric system. Okay. And one of the ways to combine different information sources, the quality of the sample, the cohort of the information, and the information that's specific to each subject. This is the user-specific information. Okay, so you can combine different sources and build a system that will a fusion system that combines different sources of information. So that's the idea behind what we're trying to do here. Okay. I'm going to skip all these details, but the way we do it is to combine the quality measures, combine some cohort analysis, which based on the other templates in the database, okay, and make use of the other template in the database to improve the system performance of a particular user. That's cohort analysis, okay, and we can make use also of the user-specific parameters. So statistically derived parameters, and then feed the information to the fusion module. Okay. The key message here is that if you combine different methods, combining the quality, you can see that we're already doing better than the baseline. If you combine all different sources of information, this is the red curve. Okay. So you're getting better performance out of different information sources. And I just want to conclude that it's important to consider different factors when measuring the system performance, as well as exploit this information to improve the system design.